Hey everybody, welcome back. Tonight we're going to talk about soil basics, and this is for my Viticulture 303 class, Harvest to Dormancy. And yeah, we're going to learn about everything that has to do with soil and dirt and why it's so important in the terms of agriculture, especially viticulture. So we have a bit of an introduction today. We'll talk about a lot of aspects of soil. So we'll talk about profiling, composition, texture, water holding capacity, and also water infiltration and drainage. And where a lot of this might seem like common sense, right? It's important to study all of these so that way we have a greater understanding of the whole ecosystem of a vineyard that we're trying to establish. It's not just the rootstocks, it's not just the grafted upper portion, right? It's a lot more, and it starts with a solid foundation of a healthy soil. You have to farm the soil to have a healthy and happy product of plants. Okay, so there's a couple of things that we look into for soil right off the bat that are extremely important. So one is the field holding capacity and drainage. Is your soil going to be able to retain enough water to let your plants live, right? Is it going to drain well enough where they can get enough oxygen in their roots and to prevent any waterlogging or decay, right? A lot of this will be determined by the texture and the organic composition of the soil that you have, right? Soil texture, by definition, is the relative amounts of sand, silt, and clay particles in your soil. So just the combination of these things will tell you like how much water it can hold, how well it drains, what nutrients might become available or what can be available to your plants, right, depending on those combinations. So another very important aspect. Next, we have organic composition, right? Organic matter is very healthy for plants and a good biota for your soil. All the fungi and mold that grows in there and all the microorganisms that live in there and contribute to the health. So organic matter is going to be very important for that. And that forms by decomposing plant and animal tissue, right? Next, we have soil profile. And this is like a wider scope image of exactly what the layers in your vineyard are down to a certain depth of different forms and compositions of soils that have formed over time through weathering and time, basically. So we'll start with soil profile first. And like I mentioned, these are layers that are formed through weathering and time. And you'll find them in just about any soils. If you dig deep enough, you'll see layers. Also, we call them horizons. And once you dig a deep enough hole, basically, you'll get a profile or kind of a greater image of the property that you're looking at before planting grapevines, right? So that's very important. So we'll start with horizons O and A. So starting at the very top, this is a generalization. It doesn't mean that everywhere on the planet has these horizons. These are just kind of like the textbook horizons. This depends on how mature your soils have become, how old they are, and if they're healthy or not, right? So generally speaking, there's an O horizon, which stands for organic layer. The organic layer is also synonymous with humus, which is like decomposed organic matter, right? So this layer is mostly organic matter, such as decomposing leaves, right? Next, we have the A horizon, which is also called topsoil. This is mostly minerals from parent material with organic matter incorporated. It's a good material for plants and organisms to live. So this is where you see like worms, beetles or anything else that's in the dirt live and thrive, fungi, right? This is also called the zone of leaching. So it's where like a lot of things leach into the soil from the surface. These layers are mostly moved by wind and water erosion. So they're very prevalent at the foothills and valleys, right? So as the mountainside erodes that parent bedrock material that's exposed, right? All of those particles fall downhill through rain, glacier movement, right? Storms, wind, right? And that'll settle at the bottom of the foothills and the valleys. So that's why we get a lot of that material settling there, right? So that ends up being the reason that valleys are often very fertile regions for agriculture, right? So you think of the Central Valley of California, you have some of the most fertile soils in all of the United States. It's like the top class certified by the USDA, which is why we can produce so much agricultural products here. So you could think about that as a good way to remember, right? Okay, so these top layers contain the most life in the soil. This is where most fungi and other small organisms are, right? So very healthy. Okay, next we have the B horizon, which is also referred to as subsoil. This is rich in minerals that leach down from A or E, but it's also known as the zone of accumulation, right? Next, we have the C horizon, which is typically a parent material, and this is weathered bedrock, the deposit at Earth's surface from which the soil developed. So this is the parent material that decomposes and then forms that looser material that the plants and organisms can live in. Then we have the R horizon, which is bedrock. This is a mass of rock, such as granite, basalt, quartzite, limestone, or sandstone, that forms the parent material for some soils. This is technically not soil, and it's located under the C horizon. So if you ever heard of anyone who was trying to establish or trying to dig on their property and they're like, man, we hit bedrock, that means it's over. Like once you hit bedrock, it's impossible to really do anything with it after that. So it's not soil. Okay, so horizons are made through weathering in time, right? We know this. What this also means is what's happening is it's being created by erosion and the incorporation of organic matter. So generally speaking, younger soils are created by tectonic plate activity and volcanic eruptions. So this is, you think of younger soils, this is how new mountains and land are created, right? So this is a lot of rock, a lot of solids coming together and forcing either a new mountain mass to form or something, right? So you think of it as these are just rocks coming together. So that is a young soil. It's immature. It's gonna be really hard for plants to thrive on that because it's mostly just it's a parent rock right now, right? Or bedrock. So it's an immature soil. Over time, as that hard rock starts to erode and decompose and form the finer materials and incorporate organic matter, that's when we start to see plants start to thrive, and then the soils get deeper and deeper over time, and then we see entire ecosystems become established, and then you get grasses, and eventually you get trees, and eventually you get like established forests at that point, and then you have a much deeper, older soil, and that can take up to millions of years to form. So that's kind of the process of how we get healthy, mature soils. Cool. So here's a picture of an example of poor versus well-drained soils and some of the bedrock that could be showing. So here on the left side, we have poorly drained soil profile. And here you can see the R horizon, this consolidated rock is exposed. It has some plants growing on the top of it, but it's a very, very thin soil profile that doesn't hold a lot of water. There's just not a lot of soil there. So we have some plants growing here, but there's not a lot of space for those roots to really establish themselves. We might have some shrubs and grasses in this area, but we wouldn't have anything large and established like trees or forests, right? We can see that a lot of the soil from this R horizon eroded and it sank down to this kind of valley at the bottom. Here we have like a very thick A horizon, lots of topsoil. It's very water saturated because as it rains, the water it seeps through this small amount of soil and then over the hillside and then down into this kind of valley that's been created. So a lot of water, so there's like a lot of nutrients, and so you see a lot of grasses formed. On the other side, we have an example of a well-drained soil profile, and for here we have a thin A horizon but a very thick E horizon, a clay-rich horizon next, and then a C horizon here where we can start to see this or parent material deteriorate, right? So we have some rock, right, but it's not a solid piece. And with this, we can see that there's a lot more capacity for this soil to have nutrients, one, to have space for roots to grow and flourish, two, and just all around create a better ecosystem that's more complete. So we see established forests, more diversity in plant life, more diversity in soil life, right, in the microorganisms present. So this is all around a well-drained soil profile in a healthier soil and more mature soil, generally speaking. So hopefully that can help put together those concepts for you guys. Here are pictures of soil horizons in the Sierra foothills, right? And there's a lot of differences depending on where you go. The soil profile here specifically is kind of bizarre, to say the least, because we have a history of hydraulic mining, and hydraulic mining happened during the gold rush where the mines weren't quite working out anymore, so now they were taking like these massive, basically the equivalent of fire hoses, blasting them into the sides of mountains to try to get to gold. Well, this was tearing apart soil from mountainsides, and then it was flooding the streams. So all this soil was being leached into local water streams, and it was pulling out toxic chemicals like arsenic and lead and other components that were in the soil. So it was like poisoning people. It was flooding the streams. It was harming local ecology and the waterfront. But then also we had created so much soil movement that we had displaced the water from our local rivers, and we actually like flooded parts of Sacramento because of that. So hydraulic mining was eventually banned, of course. Fun fact, that was actually the first environmental law passed in California, and we stopped that, thank goodness. But because of all of that movement of soil from the blasting the hillsides, we have some really bizarre soil, how it's distribution, so I'm trying to say. So we have a picture of Sacramento clay soil profile. This is near Clarksburg. And as you can see, this is just different horizons of clay compacted together. Here in Auburn near Jamestown, we can see that there's a clay loam composition, and it's not very deep because right underneath it is metamorphic rock. Then here we have Redding. This is a gravelly clay loam, and then we have a hard pan loamy sand, and then a hard pan gravelly clay loam. So a hard pan essentially is a section of soil where water cannot penetrate it. If it's a hard pan, it's so compact that water and nutrients, it just kind of rolls off the side of it, and it will find somewhere else to drain, or it could hold it in place and then just kind of stay there, basically. So ultimately the big takeaway is if you have really shallow soils, you have less water that can infiltrate, right? And then you have a limited space, and also a limited space for your roots to grow. So it's ultimately not ideal for most agriculture products. So that gets hard. Okay, that's an overview of soil profiles and horizons. Now we're going to move into soil composition. So as you saw in those soil profiles, there's these terms like clay loam, right? Gravelly clay loam, sandy clay loam, clay, like what are these things? Well, these are all a part of soil composition and soil texture, right? When we talk about soil composition, there's important things to consider. There's 4 parts. The majority of it is mineral fragments. So these are dislodged from the parent rock through weathering of some kind, right? Then up to 25% of this is actually just air, right? So soil air, including oxygen, necessary for cellular respiration of most living organisms. So we don't always think about air being important in soil, but it absolutely is. Like the roots need to breathe. There needs to be an environment for microorganisms to flourish. They'll help the soil structure. They'll also fertilize the soil. So there's a lot going on to that. About 25% of the soil composition ideally is water. And then there's also a small percentage of organic matter, which does account for both alive and decaying organisms. Okay, so the soil texture is determined by the relative amounts of these particles, right? So there's 3 types. There's sand, silt, and clay. Sand is, been to the beach, you can pick it up in your hands, right? You can see the individual grains of sand. This has the largest size of the particles, so this is between 2 to 0.5 millimeters. Silt is kind of in between. It's between 0.5 and 0.002 millimeters, excuse me. And then clay is the smallest particle size, and that's less than 0.002 millimeters. So depending on the composition of your soil, the relative amounts of these things, it's going to determine how it behaves, right? So if you are going to try to figure out what the texture of your soil is, you can do this really fun experiment where you take a sample, right? You grind it down so you can separate all of the particles from each other. You add in some soap, you mix it up in a jar, then you let it sit. Well, it'll actually separate out into the sand, silt, and clay components based off of the size of each of those particles. And then you can actually measure that and determine the percent of each of those three components. Once you find out the percentages of those things, you can use this lovely soil texture triangle to determine what the texture of your soil is, right? So you'd look at your percent sand, percent silt, percent clay. You would take a ruler and you would mark where each of those components were, right? So if you were at like 50% clay, right, you would draw a line right through here and then say, okay, well then I'm 10% silt. You would draw a line through here, and then you would take your remaining percent sand, and then you'd see where those lines intersect, and then that would give you a soil texture. So you can see a majority of this is clay. Then we have like combinations: clay loam, sandy loam, silt loam, loamy sand, right? So again, loam is just a combination of those things, but the only three types of soil texture or soil particles are clay, silt, and sand, right? Loam is a combination of those things, right? Generally speaking, loam is the healthiest type of soil for grapevines, but we have seen grapevines flourish in like sandy loam. Ultimately, we try to avoid soil that has high clay because it just holds too much water and it chokes out the roots, basically. So that's how you would determine that. So here's a picture of that jar testing method I was talking about, right, where you fill up the jar and then you put in a little bit of soap so that way it works like as a surfactant. You mix it up really good and then you let it settle overnight. Then you can measure out the percentages of each layer, right? And then you can use that triangle to determine what your soil type is. We'll actually do this for our new student demonstration vineyard for class this week, so I'm super excited. We'll be able to test multiple parts of our vineyard patch and see if it's consistent or if it differs, and then we'll be able to determine what those percentages are when we meet the following week once it all settles out. So if you would like to bring in a jar of dirt from home, you're welcome to do that as well. You'll need a good sample, probably about as much as like a coffee mug, basically, of dirt to bring it to class, and then we can determine your soil texture and type in lab as well. So that'll be something fun that we do. Okay, part 4 that's really important is water holding capacity, right? This is determined by the texture of your soil and then also the organic matter in your soil. So this will determine ultimately how much irrigation your site will need. So it's very important, right? So these things influence how much water is available to the roots of your plants. Ultimately, the higher your field capacity, the less often you'll need to irrigate your vines, right? This irrigation is a huge cost in California. So if you were going to establish a vineyard, again, for like a business, this would be a cost that you would need to calculate into running your business to make sure if you can make it or not, right? So here we have a chart and it shows the different types of soil textures, right? So we have sand. Sand doesn't hold like any water, right? Water just goes right through it. Clay holds the most water, right? So as we can see, the fineness of texture as it goes from super coarse to more fine, it holds more water. And then we can also see here on the y-axis the inches of water per foot soil depth. So this is like a measurement of the inches of water per your depth of soil, and then going from coarse to fine soil texture. And as we can see, this line traces your permanent wilting point. So if your water holding capacity of your soil drops below this line, there'll be no available water to your plant at all. So this is called the permanent wilting point. The space between that and what your field can hold is called the available water. That's the space between the permanent wilting point and then the maximum field capacity. So that's how much water your soil holds maximum. Like when it's at its full capacity, that is its field capacity. So you want to be somewhere in between these two, right? And as you can see, as we go from sand to clay, clay has the highest field capacity, right? And then you wouldn't have to really water your plants at all if you had clay. But clay is not great for vines, and we'll talk more about that. Okay, so here's another picture kind of going into field capacity and wilting point, right? So field capacity is when it's the water that adheres to the soil after water leaches through the particles. So we fully saturate the soil, all excess is pulled off through gravitational force, and it's what's left in between the particles, so it's what stays behind, right? So we have saturation, the excess comes off, and then we have field capacity. This is what stays, like I was saying, in the particles. And then the wilting point is when all of that water completely dries up. So there's zero water available to the plants, and then they're in a danger zone because that is their wilting point, right? So generally speaking, the deeper soils will retain water longer than shallow soils, right? You have more space to work with. You have more of like a savings bank to hold more water, right? Soils with high organic matter concentrations will also retain more water for a longer time. And that's because organic matter works like a sponge. It's very porous, and just the formation of it just holds water really well. Okay, let's talk about texture versus structure. We talked about texture a lot with the soil triangle, talking about sand, silt, and clay. So that is texture, right? This will affect the soil air, water retention, tilth, and is often associated with fertility of soil, right? That is different from structure because structure refers to the aggregation of soil particles into larger units, also known as PEDs, right? So if you ever like dig up some fresh soil and you see some clumps that are naturally clotted together, that's a soil PED. And that is actually really healthy for soil. We'll talk about this in the next slide, right? We'll get into more information. But PEDs can be small or granular or large and in various shapes, including platy, blocky, or column shaped. Their structure type, size, shape, and grade influence soil permeability to air, water, and roots, ultimately. So the way I think about it is texture is the components of sand, silt, and clay. It affects, a lot of water retention and soil air. Structure is how those things come together to form units. And this will help with ultimately with your health of soil and many other things as well, right? So when we talk about water infiltration and drainage, soil structure is an important indication of your healthy soils, right? So aggregates create soil structure in soil through, right, all these different things. So how these aggregates form, right, these clumps that we're talking about, right, they form through natural forces, so alternating wetting and drying, organic substances derived from root exudates, so it's just like this roots are like extracting or like pushing out these certain chemicals, these organic substances that are creating PEDs, right? Roots themselves will form aggregates as well as they kind of breach through the soil and reach around. There's also this wonderful fungi that produces glomalin. This is like this white substance that you might see as organic matter is decomposing in soil, right? Glomalin is an organic substance that will glue soil particles together into aggregates. Earthworms, other soil animals help create channels that allow gas exchange and roots to explore. So like moles, worms, other things like that will make it easier for roots to navigate through soil because it's not so compacted, right? So structure of a soil determines the ability for water to drain and to prevent it from will determine the ability for water to drain, but it will also be a sign of health to prevent erosion as well. That's what I'm trying to say. There's also a really nice article here on soil aggregate stability from the Ohio State University Extension, right? Okay, so aggregation, why is it important, right? The gluing of soil helps to maintain the pores and channels in the soil for air and water to enter and move through it, right? So this affects soil water capacity and drainage. Soil aggregates are more stable and harder to wash away than individual soil particles during rainstorms, so it helps prevent erosions. So thus, soil aggregation is an indication of health via soil structure, right? So here is just a picture to show you. On the left, we have an aggregate of soil submerged in water, and as you can see, it's holding its shape, right? It's not going anywhere. It's glued together through glomalin or other products and staying shape. However, this piece of soil on the right, this sample, once it's submerged in water, it's completely falling apart. All of the particles are sinking to the bottom. If this was, a situation where, we saw this from a rainstorm, there would just be soil spread everywhere. It would erode. It would go into new places, right? So ultimately, that's just a sign that it is not very healthy, right? And also, interestingly enough, the soil on the right is from a conventionally tilled field. So when you till a field, you actually kind of rip up the biota that is there, and it can damage the structure of that soil. You could be very careful. Okay, so here we have a picture of a well-structured soil and a poorly structured soil. This upper left one is the well-structured soil, and as you can see, there are aggregates, but there's lots of spacing between those aggregates, right? So air, water, nutrients are stored in the pores. There are large pores, right? And everything is able to kind of move freely through the soil without any problems, right? Poorly structured soil has very small pores, right? The water remains near the surface because it's having a hard time infiltrating the soil. Water and nutrients will move very slowly down the profile, and air may be excluded. So this could be a situation where it would be very difficult for a plant to grow in this environment. It would not have access to nutrients, at least very readily, and it would struggle, right? Okay, so this brings us to the concept of water infiltration, right? So to talk about structure and how it creates these channels for water and air to pass through, the component that we're looking at there is water infiltration. So what water infiltration is, it's the ability for water to pass through a system, right, of soil. So when water touches soil, it either enters the soil, also known as infiltration, or it runs off the soil surface, right? If you have compaction, soil that is less porous, it'll have a difficult time infiltrating, right? So difficult percolation and evaporation. The runoff leads to erosion and flooding, and you'll have difficult root penetration of your plants, right? So no moisture, no air, difficult for your roots to prosper and to grow. If you have a less disturbed soil, you generally have more porosity, so more space for better water infiltration. You'll have less runoff than in heavily disturbed soils. So generally speaking, it'll be a lot healthier, happier time, right? Okay, perfect. Okay, so we have water infiltration. How do we determine water infiltration? Well, we look at the amount of compaction, right, of your soil. So when you think of compaction versus a less disturbed, healthier soil, you're thinking about the density, or like the amount of soil crammed into one space or to one volume, right? So to determine that, we determine something called bulk density, right? So generally speaking, here's the thought process. A soil with less organic matter will contain less aggregates. The lack of soil structure will mean that there's less pores, so less infiltration, right? This means you have high density soil, which means you have a high instance of compaction. It's very tight. It's very difficult for anything to get through or to thrive in this situation, right? So we measure this through bulk density. It's a measure of soil compaction or lack of porosity. So for this, we're actually going to do this in class. We're going to determine the weight We're going to take a soil sample and we're going to take it from a measured volume in the ground. We'll take the weight of the soil sample as it is. We'll subtract it from the dry soil sample. So we have to take into account any water that might be present. And that will give us a value in grams per centimeters cubed. We can reference the soil texture, and then we can see what the ideal bulk density of that space would be for plant growth, right? So if it's a sandy soil texture, if it's less than 1.60 grams per centimeters cubed, that's ideal for plant growth. If it's greater than 1.80, that will restrict your root growth. So this is a way to quantify exactly how much density or how much compaction is unhealthy for your soil and for your plants, depending on the specific soil structure you are working with, right? And as you can see, as we get into more clay-like soils, there's less of a tolerance for bulk density. It drops to less than 1.10 in that case, where there's more of a tolerance for sand because of its texture, right? So hopefully that makes sense, right? Okay, so what does soil compaction look like in a vineyard? It looks like this. So after something's been irrigated, or maybe there's a rain, where you see where this tractor has gone through next to this vineyard, you can see how the soil has hardened, and you can see how there's puddles left behind, right? So if you see water accumulating at the surface and not draining, it's high compaction, but also could be high clay, right? So there's very little to no pores or options for that water to pass through the soil, right? So soil compaction, the process of soil particles being pressed together, which reduces the pore space between them. So this will decrease your water infiltration, limit root development and scavenging for nutrients and water, imposes unnecessary drought and nutrient stress on vines, will reduce your vine growth and healthy microbial activity, and it increases superficial flooding and erosion. So, not a good time. Okay, so where does the water go, essentially? So water that comes through the sky through rain, precipitation, or irrigation does not stay in the soil, right? It's either percolated down to the water table through gravity, also known as drainage. It can be released back into the atmosphere through evapotranspiration. Evapotranspiration is just a fancy word for a combination of evaporation and transpiration, right? So it's the combination of water transpired by plants as they photosynthesize and the water that evaporates from the soil surface as well. So the water that is held in the soil field capacity is available for the plant to consume and also for evapotranspiration. So that's where all the water is going. Okay, so these are a couple images to determine bulk density and the ability for your soil to have the capacity it has to let water infiltrate. Bulk density, we take a solid ring, and we hammer it down very carefully into a soil sample. We know the volume of that ring based off of certain calculations, right? Then we weigh the soil as it is, we bake it, weigh it dry, and then we can determine the density of that soil, right? So this is the bulk density test. Below it, we have the infiltration test, and for this we also utilize a ring, but we also put down some saran wrap, and then we fill it with a certain amount of water. Once we're ready with a timer, we'll remove that saran wrap, and then we will time how quickly or how slowly it takes for that water to pass through the soil, through the ring. So this will tell us essentially like what is the rate of infiltration of water, right? So overall, relatively straightforward once you wrap your mind around it, but these are tests that have been used and will continue to be used for centuries because they give us the data that we need on soil. So very, very helpful. Okay, and if you really want to geek out on soil, I have a couple of really fun resources for you. So we have the UC Davis Soil Resource Lab and the USDA Web Soil Survey. So if you want to know exactly what soil you have on your property, on certain parts of viticulture regions across California, the United States, This is a Google mapping system that will literally tell you what types of soils are in each section, what they're composed of, what their texture is, what the slope is, what the parent material is. It's extremely in-depth and detail. There's also a free app you can get on your phone, and it's called, I think it's just called Soil Maps. Let me just double check really quick. Oh, Web Soil Survey. Right. So once you open this up, you would look into an area of interest, right? You could go to soil map. Oh, excuse me. You'd have to put in your area of interest. You could search an address. You could search like a general region. Then you could zoom in and you could see exactly what types of soils are there. I was able to use this at Boger to help them with understand which soils were in which parts of the vineyard. And it was very interesting and very informative. So we have these resources for you guys here. And then finally, we have our student learning objectives. This will help prepare you for the quiz. I hope this was helpful. If you have any questions, don't hesitate to email me. But overall, thank you for listening, and I look forward to seeing you guys next time.